Welcome to another deep dive, and today we're going on a bit of a journey. I know you're all really into machine learning and data science and math, and we're going to explore a really cool spot where those all come together, image captioning.
Yeah.
We're going to be breaking down a pretty massive survey paper on this. It really maps out image captioning, kind of how it started, all the way to the incredible advancements we've seen, especially thanks to deep learning.
Yeah.
And we've got an awesome expert here with us today who's going to be kind of walking us through the gnarly parts of this research.
Right.
Um, they are incredible at breaking down complex stuff. And honestly, they're just as excited about this as I am.
Absolutely.
So before we get into the weeds of the technical details, let's kind of set the stage here.
Okay.
So image captioning, what is it? It's basically teaching AI to look at an image and describe it to us in, like, natural language.
Right.
It's like giving computers the ability to see and then explain to us what they're seeing, almost like we would do, right? And this is so much more than just, like, picking out objects in an image.
Yeah.
It's about understanding how those objects relate to each other, what's going on in the picture, and then putting it all into words in a way that makes sense.
Yeah, like creating a narrative.
Yeah. Exactly. It's like AI storytelling. And here's why I think this is super cool, especially for you, with your expertise and all. This isn't just some fancy tech demo. Image captioning can change everything from, like tools for people who can't see to how we make content and even how our own brains process, like, visual information.
Yeah. It's pretty mind-blowing when you think about
Yeah,
it.
yes, it is.
Yeah.
So are you ready to dive in?
Let's do it. Let's start with a little bit of history. Image captioning has actually been around for a while. Before deep learning was even a thing, people were trying to figure out how to make computers describe images. One of the early ways they did it was with something called description retrieval. It's kind of like doing a reverse image search, but instead of finding similar pictures, you're finding pictures with similar descriptions.
Oh, so you'd have a database of images and captions, and you'd search for captions that match the image you're trying to describe.
Exactly. Another early approach was template filling. You know those Mad Libs games where you fill in the blanks to make a funny sentence?
Ah, yeah, I remember those.
Researchers would create templates with slots for objects, actions, and attributes, and then try to fill in those slots based on what they saw in the image.
Oh, that's interesting. But I can imagine those methods were pretty limited in what they could do.
Yeah, you're right. They weren't very flexible or nuanced, so they couldn't really capture the complexity of real-world images.
Right, they couldn't really deal with new objects or scenes that didn't fit their predefined templates.
Exactly. And that's where deep learning completely changed the game.
Right, right.
With deep learning, models can learn complex patterns from tons of data. And that opened up a whole new world of possibilities for image captioning.
Yeah, it's like going from a simple rule-based system to a system that can actually learn and adapt on its own.
Yeah, exactly. And with deep learning, we see two key components emerge: visual encoding and language modeling.
Okay.
Visual encoding is how we turn the raw pixels of an image into something that a deep learning model can understand.
Right.
It's like translating the visual world into the AI's language.
Okay, so the computer needs to be able to see the way we see it, or at least in a way it can understand it.
Exactly, yeah. And then you have language modeling, which is about generating those natural language descriptions. It's teaching the AI how to put words together in a way that makes sense, grammatically correct, and meaningful, just like a human writer would.
Wow, so the AI needs to be both an artist and a writer at the same time. It needs to see the image and then write about it.
That's a great way to put it. And that's where the research paper goes into all the different visual encoding strategies that researchers have explored.
Okay, lead the way. I'm ready to get into the details of how these AI systems actually see the images.
Let's start with one of the simplest approaches, using global CNN features. Basically, you take a pre-trained convolutional neural network, CNN, something like GoogleNet, and you use it to extract a single feature vector that represents the whole image. This vector captures the overall gist of the image, like what objects are there and what kind of scene it is.
I see. So it's like boiling the entire image down to its essence, a single vector that represents the big picture.
Exactly. One of the early models that used this approach was called show and tell. It was a big deal because it showed that deep learning could actually generate somewhat coherent image descriptions. But it was also clear that this approach had its limits.
Well, yeah, I can imagine that compressing an entire image down to a single vector would mean you lose a lot of the finer details, right? Like, you might know there's a cat in a tree in the picture, But you wouldn't know if the cat is sleeping under the tree or chasing a squirrel up the tree.
You're exactly right. That's the trade-off with this approach. You gain simplicity, but you lose detail.
So how do you get the AI to pay attention to those finer details without getting overwhelmed by too much information?
That's where attention mechanisms come into play.
Oh, attention mechanisms. I've heard that term thrown around a lot. What exactly does that mean in the context of image captioning?
Well, one early method was called attention over grids. Instead of representing the whole image as one big vector, you divide the image into a grid and extract features for each cell in that grid.
Okay, so you're breaking the image down into smaller chunks, making it more manageable for the AI to process.
Exactly. And then the AI learns to focus on specific cells in that grid that are most relevant to the caption it's trying to create. It's like the AI is shining a spotlight on the most important parts of the image.
So it's not just blindly processing everything in the image, it's learning to be selective, to prioritize the information that matters most.
Exactly. And a really cool paper by Zhu et al. Introduced something called additive attention. This allowed the model to shift its focus as it generated each word of the caption. It's like the AI is actually reading the image, scanning it for the most relevant information as it constructs the caption.
That's fascinating. It's almost like the AI is learning to see the way we do, focusing on the most salient parts of the scene.
And then it gets even more interesting when we move beyond grids and start using object detectors to identify specific regions of interest.
Object detectors. So now we're talking about AI systems that can actually recognize specific objects in an image, like cats, dogs, cars, trees, and so on.
You got it. And this is what we call attention over regions. Instead of attending to arbitrary grid cells, the AI now focuses on regions that actually correspond to objects in the image.
Okay, so instead of just focusing on a random patch of pixels, the AI knows that this patch represents a cat and this other patch represents a tree.
Precisely. And this allows the AI to generate much more detailed and specific descriptions because it can analyze each object individually and take into account its unique characteristics. For example, instead of just saying there's a cat in a tree, it might say, a fluffy gray cat is perched on a branch of a tall oak tree.
I see. So it's not just describing the scene in general terms. It's able to provide a much richer and more nuanced narrative by focusing on the individual elements within that scene.
Exactly. One of the key papers that really demonstrated the power of this approach was by Anderson et al. They used a faster RCNN object detector to We're still just scratching the surface of what's possible.
Oh, really? What else is there? It seems like we're making great progress already.
Well, while this approach lets us focus on individual objects, it still doesn't capture how those objects relate to each other. It doesn't tell us how they interact or how they contribute to the overall story of the image.
Ah, I see. So you might be able to identify the cat and the ball, but you still wouldn't necessarily understand that the cat is playing with the ball. And that's a crucial part of the story.
Exactly. And that's where the next level of visual encoding techniques comes in, and that's what we'll be exploring next. So to really understand those relationships, researchers started looking at graph-based encoding. It's this really cool idea of using graphs, kind of like those diagrams with nodes and edges, to represent the connections between objects in an image. It's like creating a visual sentence out of the image.
Oh, that's interesting. So you're not just treating objects in isolation anymore. You're actually mapping out their relationships, like who's doing what to whom.
Exactly. The research paper dives into different ways to do this. One way is using what they call scene graphs.
Scene graphs, okay.
Yeah, so in a scene graph, each object in the image is a node, and the relationships between those objects are the edges connecting the nodes.
So if you had an image of a cat sitting on a mat, the cat and the mat would be nodes, and the sitting on relationship would be an edge connecting them.
Exactly. And then you have other types of graphs like spatial and semantic graphs. These incorporate not only the spatial relationships between objects like above or below, but also semantic relationships like wearing or holding.
Oh, that makes sense.
Yeah.
So you're not just capturing where things are in the image, but also how they're interacting with each other on a more meaningful level.
Right. And this richer representation allows the AI to generate captions that are not only accurate, but also more well-rounded, I guess.
More contextually relevant, maybe?
Yeah, exactly. They tell a more complete story about what's happening in the image.
Okay, I'm starting to see how powerful this graph-based approach can be. But how do you actually use these graphs to generate captions?
Well, there are different techniques for that. Some researchers use graph convolutional networks, or GCNs, which are specifically designed to operate on graph-structured data. Others use recurrent neural networks, or RNNs, with attention mechanisms that allow the AI to focus on specific parts of the graph.
So it's about combining the power of graph representations with the flexibility of deep learning architectures like GCNs and RNNs.
Yeah, and then there's another really exciting development that's kind of taken the field by storm: self-attention mechanisms and the transformer revolution.
Transformers, yeah, those are all the rage in NLP these days. But how do they apply to image captioning?
Well, instead of attending to words in a sentence, the transformer attends to image features, letting it model relationships between all parts of the image at the same time.
Okay, so it's like the transformer is looking at the whole picture at once, rather than focusing on one part at a time.
Yeah, and this allows it to capture more complex and subtle relationships between objects.
So it's kind of like how we humans perceive a scene. We don't just focus on one object at a time. We take in the whole scene and understand how everything fits together.
Right. And some really cool examples of this are mesh decoders and geometry-aware encodings.
Those sound pretty complex.
They can be, but they've led to some really impressive results.
I can imagine. And then there's image-text early fusion, right?
Right. So that's another fascinating approach that the paper talks about.
I've heard about that. It's where you process visual and textual information together right from the start,
Right.
instead of treating them as separate steps.
Exactly. You have models like Oscar and VinVL, which are kind of like BERT, but for both images and text.
Oh, BERT. Yeah, that's the model that's been making waves in natural language processing.
Right. So instead of first encoding the image and then feeding that into a language model, these models process everything together, which lets them learn richer representations that capture the interplay between vision and language.
It's like they're learning to think in both visual and textual terms at the same time, rather than having to translate between the two.
Yeah, that's a great way to put it. And this has been really promising, especially for tasks that require a deeper understanding of how images and text relate to each other.
That's amazing. We've talked a lot about how these models encode visual information. But what about the other side of the coin? Actually generating the caption itself.
Right, so that's where language modeling comes in.
Lead the way. I'm curious to hear how these models actually craft the narrative.
For a long time, the most common approach was using LSTM-based models. LSTMs, or long short-term memory networks, are a type of recurrent neural network specifically designed to handle sequential data like text.
Oh, LSTMs. I remember learning about those in my deep learning course. They're pretty good at remembering things over time, which is important for generating coherent text.
Exactly. And they were trained on huge data sets of image caption pairs, learning to predict the next word in a sequence based on the image and the words that came before.
So they're kind of like autocomplete, but for captions.
Yeah, in a way. But LSTMs can be slow to train, and they sometimes struggle with long sentences because they can lose track of the context.
So did researchers explore other architectures to try to overcome those limitations?
They did. One alternative was using convolutional language models, which use convolutional neural networks to process words in parallel.
Convolutional neural networks, those are usually used for image processing, right?
Right, but they can be adapted for language modeling as well. And while they didn't outperform LSTMs in terms of quality, they were much faster because of the parallel processing.
Speed is always a good thing, especially when you're dealing with lots of data.
Absolutely. But ultimately, the biggest breakthrough came with, you guessed it, transformers.
Transformers again. It seems like they're everywhere these days.
They really are. And just like in NLP, they revolutionized language modeling for image captioning. With their self-attention mechanisms, they're really good at capturing long-range dependencies in text, which means they can generate more coherent and fluent captions.
So they're not just better at understanding individual words. They're better at understanding how those words fit together in a sentence and how those sentences fit together in a story.
Exactly. Some of the specific techniques being used include masked self-attention, where the model tries to predict missing words in a sentence, and gating mechanisms, which control the flow of information within the transformer.
It's amazing how these techniques, which were originally developed for NLP, are now being applied to image captioning.
Yeah, and we also see the influence of BERT-like models here.
BERT is showing up everywhere, isn't it?
It really is. Just like with visual encoding, we have image-text early fusion models that use BERT-like architectures to generate captions directly from their joint visual textual representation.
So BERT isn't just about understanding text anymore. It's becoming a multi-modal powerhouse.
Exactly. And then there's another interesting area that's starting to emerge: non-autoregressive language models. These models aim to generate all the words in the caption simultaneously, rather than one word at a time.
Wow, parallel caption generation. That sounds like it could be a lot faster.
It could be, but it's also a much harder problem to solve. But the potential benefits in terms of speed and efficiency are driving a lot of research in this area.
So far, we've covered how these models encode the image and generate the caption, but how do we actually train them to do all this?
Right, so that's where training strategies come in.
Let's dive into those and see how we teach these AI systems to be storytellers.
Okay, so one of the most common approaches is using something called cross-entropy loss. It's a classic technique where you basically try to minimize the difference between the words the AI predicts and the actual words in the captions from the training data.
So you're essentially rewarding the AI when it gets the words right and penalizing it when it gets them wrong.
Exactly. But this approach can lead to captions that are kind of boring and repetitive because the AI is just trying to mimic the training data as closely as possible.
Right. You want the AI to be creative and come up with its own unique descriptions, not just parrot what it's seen before.
Exactly. So researchers have explored other techniques like masked language model training, which is what BERT uses.
BERT again.
It's everywhere. So with masked language modeling, you randomly mask out some of the words in the captions and then train the AI to predict those missing words based on the context.
It's like a fill-in-the-blanks exercise for the AI.
Exactly. And this has been shown to improve the quality, fluency, and diversity of the captions.
So it's not just about getting the right words, it's about getting the right words in a way that sounds natural and interesting.
Right. And then you have reinforcement learning, where you train the AI to generate captions that score well on specific evaluation metrics, like the CIDR score.
So you're not just training the AI to predict words, you're training it to generate captions that are judged to be high quality, according to these metrics.
Exactly. And this has been really successful in pushing image captioning models to generate captions that are not only grammatically correct, but also more relevant and meaningful. But one of the biggest advancements in recent years has been large-scale pre-training.
Large-scale pre-training, what's that?
So instead of training the model from scratch on a specific image captioning data set, you first train it on a massive data set of images and text, like, stuff scraped from the internet.
So you're giving the AI a huge amount of general knowledge about the world before you even start training it on the specific task of image captioning.
Right. This way, the model learns to recognize a wide range of objects, scenes, and actions, and how those are typically described in language. Then you can fine-tune it on a smaller, more specific data set for image captioning.
It's like giving the AI a crash course in visual storytelling before you send it off to write its own captions.
Exactly. And examples of these pre-trained models include conceptual captions and SBU captions.
So those are like the star pupils of the image captioning world, having benefited from this intense pre-training.
You could say that.
Okay, we've talked about how these models are trained, but how do we actually evaluate how well they're doing? How do we judge the quality of these AI-generated captions? I mean, it can't just be about checking for spelling and grammar, right?
Right, it's definitely more than that.
So how do we measure the success of these AI storytellers? What are the benchmarks?
Well, the paper goes into a lot of detail about different evaluation metrics that have been developed over the years.
Okay, let's get into those. I'm curious to see how we can quantify something as subjective as storytelling.
Well, some of the early metrics were borrowed from other NLP tasks, like machine translation and summarization.
Oh, so we're adapting existing tools to measure the quality of these captions. Makes sense.
Yeah, so, for example, you have BLU, which was originally designed to evaluate machine translations. It basically looks at how many words in the generated caption match words in a set of reference captions.
So it's a measure of how closely the AI's caption aligns with what a human would say.
Exactly. And then you have Meteor, which goes a bit deeper and considers the alignment of words in terms of both meaning and form.
So it's not just about matching words verbatim, it's about capturing the semantic similarity as well.
Right. And then there's Rouge, which is commonly used for evaluating summaries. It measures the overlap of longer sequences of words, or what they call n-grams.
So it's looking for chunks of meaning that are shared between the generated caption and the reference captions.
Exactly. But then you also have metrics that were specifically designed for image captioning, like CIDR and SPICE.
CIDR and SPICE, what do those stand for?
CIDR stands for Consensus-Based Image Description Evaluation, and it basically measures how similar the generated caption is to a consensus of human-written captions.
So it's comparing the AI's caption to what a group of humans would say, rather than just one individual human.
Right. And then SPICY, which stands for Semantic Propositional Image Caption Evaluation, focuses on the semantic content of the caption, making sure it aligns with the objects, actions, and relationships depicted in the image.
Ah, so Spice is really focused on whether the AI is capturing the essence of the story in the image, rather than just spitting out grammatically correct sentences.
Exactly. It goes beyond just surface-level word matching and looks at the meaning behind the words.
That makes sense.
Yeah.
But even with all these metrics, aren't we still missing something? I mean, two people can describe the same image in completely different ways, and both descriptions could be perfectly valid.
You're right. And that's why researchers have started exploring something called diversity metrics.
Diversity metrics. Okay, I like where this is going. Tell me more.
So these metrics try to measure how varied and creative the generated captions are. The goal is to encourage the AI to come up with different ways of describing the same image rather than just sticking to the most common or obvious description.
It's like we're trying to push the AI to be more expressive, more human-like in its storytelling.
Exactly. So some of these diversity metrics look at the number of unique words used, the percentage of captions that are novel, meaning they weren't in the training data, and the ratio of unique unigrams and bigrams, which tells you how repetitive the AI is being.
It's really fascinating how we're trying to quantify something as elusive as creativity. But the quest for better evaluation doesn't stop there. The paper also talks about embedding-based metrics that use word embeddings to assess things like alignment, coverage, and relevance.
Right, so word embeddings are these mathematical representations of words that capture their meaning.
So we're moving beyond just comparing words at a surface level and actually looking at their underlying semantic meaning.
Exactly. So, for example, the word mover's distance metric measures the semantic distance between the generated caption and the reference caption, taking into account the meaning of the words rather than just their surface form.
It's like we're trying to teach these evaluation metrics to read the image through the language of the caption.
Exactly. And then you have the coverage score, which measures how well the caption covers the important visual elements in the image.
So it's making sure the AI isn't missing any key details.
Right. And finally, we have the emergence of something called learning-based evaluation.
Learning-based evaluation, what is that?
So this is where we use pre-trained language models, like BERT, to evaluate the quality of the captions.
So we're bringing in the big guns of AI to judge the work of other AI systems.
Exactly. These pre-trained models, with all their knowledge of language and how it relates to the world, are being used to assess captions in a more sophisticated way than traditional metrics can.
So instead of just relying on simple word matching or statistical measures, we're now leveraging the power of deep learning to evaluate captions in a more nuanced and human-like way.
Right. Some examples of these learning-based metrics include the BERT score, the Tiger score, and the CLIP-S score.
Still sound pretty technical.
They are, but they're pushing the boundaries of how we evaluate image captions. And the really exciting thing about learning-based evaluation is that it has the potential to move beyond the need for reference captions altogether. For example, the CLIP-S score uses the CLI model, which was trained on a massive data set of images and text, to directly assess how well a caption matches an image without relying on any human-written captions.
Wow. So we're moving towards a world where AI can judge its own creative output based on its own understanding of how images and language relate to each other.
Exactly, and this opens up a whole new world of possibilities for image captioning.
So far, we've focused on the core techniques of image captioning. But the paper also talks about all these different variations and applications, right?
Right. Image captioning is not just about generating a single caption for a single image. There's a whole universe of specialized tasks and applications that researchers are exploring.
Okay, now we're talking. Let's dive into those and see how image captioning is being used to solve specific problems and push the boundaries of what's possible.
One really interesting area is novel object captioning. This is where you train the AI to describe objects that it's never seen before.
That sounds like a challenge. How can an AI describe something it doesn't even know exists?
Well, researchers have come up with some clever ways to tackle this problem. One approach is to create a special version of the CoECO dataset, which is one of the most common datasets used for image captioning, where they remove certain object classes from the training data but keep them in the test set.
So the AI never sees those objects during training, but then it has to describe them during testing. It's like a pop quiz for the AI.
Exactly. And another approach is to incorporate something called copying mechanisms into the models.
Copying mechanisms, what are those?
So these mechanisms allow the AI to borrow words from external sources like object tags or even captions from other datasets to describe these novel objects.
Ah, so it's like giving the AI access to a dictionary or encyclopedia to help it fill in the gaps in its knowledge.
Exactly. And then there's the NoCaps dataset, which was specifically designed to test the AI's ability to handle novel objects. It has nearly 400 object classes that the AI has never seen before.
Wow, that sounds like a tough challenge.
It is. And to help the AI do well on this task, researchers are using techniques like constrained beam search, which is a way to control the AI's output and make sure it includes specific object labels in the caption.
So you're giving the AI some hints, but you're still letting it be creative and come up with its own way of describing the scene.
Right. And with the rise of BERT-like architectures, we're also seeing pre-training strategies that involve masking out object tags and training the AI to predict those missing tags. This helps the AI learn more robust and generalizable representations of objects, even ones it hasn't explicitly encountered before.
It's like we're training the AI to be a detective, piecing together clues to identify and describe these mysterious new objects.
That's a great analogy, but novel object captioning is just one example. What about situations where you don't even have any paired image caption data to train the model?
Wait, so you're saying you can train an AI to generate captions without any captions to learn from? That sounds impossible.
Yes. Well, it's not impossible, it's just really hard. It's called unpaired image captioning, and it's a very active area of research.
Okay, color me intrigued. How does that even work?
Well, there are a couple of main approaches. One is unsupervised learning, where you try to leverage other sources of information to guide the caption generation process. Early work in this area explored using a pivot language, where the AI would generate a caption in a different language and then translate it to the target language. But more recently, the focus has shifted to using adversarial learning, with something called generative adversarial networks, or GANs.
Ah, GANs. Those are the models that can generate realistic images, videos, and even music, right? Are we applying those to captions now?
We are. So with GANs, you have two competing AI models. A generator, which tries to create captions, and a discriminator, which tries to distinguish between real captions and generated captions.
It's like a game of cat and mouse, where the generator is constantly trying to fool the discriminator into thinking its captions are real.
Exactly. And through this process, the generator gets better and better at creating realistic captions.
So you're basically training the AI to be a master forger of language.
You could say that. Other approaches to unpaired image captioning involve using scene graphs as a starting point, leveraging the structured representation of the image to guide the caption generation process. There are also methods that use memory-based networks, where the AI stores and retrieves information from a memory bank to help it generate captions.
Wow, so many creative approaches. It's really impressive to see how researchers are finding ways to train these models, even without having the traditional paired data. But it's not just about dealing with limited data. Researchers are also exploring ways to make those captions richer, more descriptive, and engaging.
Yeah, absolutely. There are a lot of really cool variations on the basic image captioning task.
Okay, tell me about those. Let's go beyond the basics.
One area that's really gaining traction is dense captioning. This is where, instead of generating one caption for the whole image, the AI generates descriptions for multiple regions or objects within the image.
Oh, that's interesting. So it's like the AI is providing a more detailed and nuanced commentary on the image, highlighting specific points of interest.
Exactly. It's like having an AI tour guide walk you through the image and point out all the interesting details.
I can see how that would be useful for images with a lot going on, like a busy street scene or a complex scientific diagram.
Right. And it's also valuable for applications like image search, where you want to find images based on specific details.
So dense captioning is all about adding a whole new level of depth to image description. What else is there?
Well, if dense captioning is about adding depth, then visual storytelling is about adding sequence. Instead of just describing individual images, the AI generates a series of captions that narrate a story based on a sequence of images.
Wow. So the AI is actually creating a comic book or a short film using words. It's taking on the role of a screenwriter or a novelist.
Exactly. And this has huge potential for applications like photo albums, security camera footage, or even animated movies.
This is mind-blowing. It's like AI is graduating from being a mere describer to becoming a true storyteller.
And the journey into storytelling doesn't end there. We also have diverse captioning, where the goal is to generate multiple distinct captions for the same image.
That makes sense. I mean, if you ask 10 different people to describe the same image, you'd probably get 10 different captions, all of which could be considered good in their own way.
Right. And diverse captioning aims to replicate that same richness and variability of human expression.
So it's not about finding the one right caption. It's about exploring the full spectrum of possible interpretations.
Exactly. And to do this, researchers are modifying beam search algorithms, using conditional jams, and even leveraging paraphrasing techniques.
It's like we're trying to unlock the AI's imagination and encourage it to think outside the box.
And it's not just about creativity. Researchers are also working on making image captioning more accessible and inclusive.
Oh, that's great. How are they doing that?
Well, one area that's getting a lot of attention is multilingual captioning. The goal is to extend image captioning beyond English and enable the generation of captions in many different languages.
That's fantastic. Image captioning could be a powerful tool for breaking down language barriers and making information more accessible to people around the world.
Absolutely. There are two main approaches to this. Training models on datasets with captions in multiple languages so they can translate between languages, or training models that can directly generate captions in different languages without relying on translation.
So we're training AI to be a multilingual storyteller capable of communicating with a global audience.
Exactly. And as the field continues to evolve, we're seeing image captioning being applied to increasingly specialized tasks tailored to specific applications or domains.
Okay, give me some examples. I'm curious to hear how this technology is making its way into the real world.
One exciting area is medical image analysis, where AI is being used to generate reports from scans and other medical images.
Oh, wow. So AI is helping doctors diagnose and treat patients more effectively.
Exactly. Another growing area is art description, where the AI is trained to not only describe the visual elements of a painting or sculpture, but also capture its style, context, and even the artist's intentions.
It's like we're training AI to be an art critic.
Yeah, it's pretty amazing. And we're also seeing applications in journalism, where AI is used to generate captions for news images, helping to automate content creation and make news more accessible.
The possibilities seem endless. It's like image captioning is finding its way into every corner of our lives.
And as we continue to push the boundaries of this technology, we're likely to see even more creative and impactful applications emerge. But there's one final category of image captioning tasks that I think you'll find particularly interesting, given your background in machine learning.
Oh, okay. You've got me hooked. Tell me more.
It's all about putting the user in control. It's about giving them the power to personalize and guide the caption generation process. Personalized AI. I love it. Tailoring the experience to individual needs and preferences.
Exactly. One area that's getting a lot of traction is personalized captioning, where the AI learns to describe images in a way that's specific to the individual user, taking into account their preferences, vocabulary, and even their writing style.
So instead of generating generic captions, the AI is learning to speak in the user's voice.
Exactly. Early work in this area used memory networks to store user-specific information, but now we're seeing more sophisticated approaches using multi-modal transformer networks that can personalize captions based on the user's past captions or even a learned representation of their personality.
That's incredible. It's like the AI is becoming your personal storyteller, adapting to your unique way of seeing and describing the world.
And then we have controllable captioning, which takes personalization a step further. This allows users to directly guide the caption generation process, telling the AI what aspects of the image they want to focus on or what kind of information they want the caption to convey. So instead of just being passive consumers of captions, users are becoming active participants in shaping the narrative.
Right. Users might select specific regions of the image they want described, provide keywords, or even draw a path through the image for the AI to follow.
It's like having a conversation with the AI, collaborating to tell the story.
Exactly. And finally, there's image captioning editing, where the AI is given the opportunity to revise its own work, correcting mistakes, adding details, or adjusting the style.
So it's like having an AI writing partner who can help you polish your captions.
We've really journeyed through a comprehensive overview of the field, from the core techniques to the challenges, the cutting-edge trends, and all these amazing applications. But where do we go from here? What does the future hold for image captioning? The research paper outlines some interesting future directions.
Yeah, it's a really exciting time to be working in this field. One of the biggest themes that comes up again and again in the paper is the need for more data.
More data, of course. Data is the fuel that drives AI. Exactly. And as we develop these increasingly complex image captioning models, they're just getting hungrier and hungrier for data. They need vast and diverse data sets to learn from.
It makes sense. The more examples they see, the better they can capture the nuances of visual storytelling.
Right. So the paper talks a lot about exploring new ways to collect data, like maybe leveraging crowdsourcing or web scraping to gather images and captions from the real world, making sure we have a wide range of visual and linguistic styles represented.
So it's not just about quantity, but also quality and diversity.
Exactly. And then there's the whole issue of computing power.
Ah, yes. The eternal struggle for more processing power.
It never ends. But it's really important because these models are becoming increasingly complex and computationally demanding. The paper highlights the need for continuous advancements in both hardware and software to keep up with the growing demands of image captioning.
So we need faster processors, more memory, and better algorithms to train these AI storytellers effectively.
Right. And as we develop these more powerful models, we also need to be very mindful of potential biases.
Biases. How do those come into play in image captioning?
Well, just like with any AI system, image captioning models can inherit biases from the data they're trained on.
So if the training data is skewed in a certain way, the model might learn to generate captions that reflect those biases.
Exactly. For example, if the training data mostly shows images of people from a particular demographic, the model might struggle to generate accurate and appropriate captions for images of people from other demographics.
That's a really important point. We need to make sure these systems are fair and inclusive, not perpetuating existing stereotypes or biases.
Absolutely. The paper stresses the importance of developing methods to both mitigate bias in the data itself and also in the models trained on that data.
So it's a two-pronged approach, making sure the data is representative and also making sure the models are trained in a way that minimizes bias.
Right. And there's also a growing interest in exploring how image captioning can be used for social good.
Oh, that's fantastic. How so?
Well, one area that has a lot of potential is accessibility. Image captioning can be used to generate descriptions for images that are accessible to people with visual impairments, allowing them to experience visual content that would otherwise be inaccessible.
That's amazing. It's like we're giving people who are blind or visually impaired a
Yeah.
way to see through the power of language.
Exactly. And there are also potential applications in education where image captioning could be used to create more interactive and engaging learning materials.
Wow, so many possibilities. It's really inspiring to see how this technology can be used to make a positive impact on the world.
It really is. Image captioning is this really fascinating field at the intersection of computer vision and natural language processing, and it's just exploding with new ideas and applications.
It's been an amazing journey exploring this with you. I feel like I have a much deeper understanding of this field now. But before we wrap up, I'm curious, is there one big question that the paper leaves us with?
As image captioning models become increasingly capable of generating these human quality descriptions, it raises a really fundamental question. Are these systems truly understanding the images they're describing, or are they just really good at mimicking human language?
It's the age-old question of artificial intelligence, isn't it?
Yeah.
Are we creating machines that truly think, or are we just creating machines that are incredibly good at simulating thought?
Right. And that question becomes even more relevant as image captioning blurs the line between human and machine.
It's definitely a question that will continue to fuel research and debate for many years to come.
Absolutely. And as we develop these technologies further, it's crucial that we keep these big questions in mind, ensuring that we're building AI systems responsibly and thoughtfully.
Well said. So let's wrap up our deep dive into image captioning with some key takeaways. Image captioning is a rapidly evolving field, driven by the power of deep learning. It's not just about generating single captions anymore. We have all these incredible variations like novel object captioning, unpaired image captioning, dense captioning, visual storytelling, and personalized captioning. We're seeing the emergence of more sophisticated evaluation methods, including those that use pre-trained language models like BERT. And we're starting to see image captioning being used for social good, making information more accessible and breaking down language barriers. It's a really exciting time to be following this field, and I, for one, can't wait to see what the future holds. Thanks for joining us on this deep dive, and we'll see you next time.